All right. So this is sometimes in the lab, inadvertently, one ends up getting an interesting situation, which can be a learning opportunity for all of us, okay? So this is a circuit here, right? All of you have made this particular circuit in the lab. A resistor, a diode, and this, right? And we know that the current flowing from here will flow through the diode. And if the circuit has been made properly, I should get a negative voltage here, right? Which is a negative diode drop, right? So if I run my simulation, right? So this is what I get. And in the lab also, we get something similar. Minus 620, minus 630, or whatever it is, right? So this is how it's supposed to work. So one group of students in the lab, they made a circuit like this, right? A similar circuit, I'm not saying identical. So I'll show you the circuit. Right, they made the circuit like this, and this is what they got. Can you see? What are they getting at the output? They were getting some positive voltage. We just saw that you should get a negative voltage. Minus 630, minus whatever, minus diode drop, right? They were getting some positive voltage. All right, so they were getting this positive voltage. They said something is wrong with the circuit. Obviously, something is wrong with the circuit. They took out the op-amp. Okay, guesswork. Well, probably the resistors don't go bad. Diode is also very robust. Maybe the most unreliable component in the lab is the op-amp. So take it out, right? Take it out. Also, it has more connections. Maybe you have not inserted properly. Take out the op-amp and they put it back. And again, the same thing. Right? Again, the same thing. So now what do? Well, you check the polarity of the diode. Is the diode connected right? It's still the same thing. Right? So we looked at it. And so the issue was what could be wrong, you know? So the why is this behaving in this particular manner here? So, you know, if you look at it, it's positive. So, you know, when circuits like this, why do they go bad? Many times they don't give you the right result. So the thing is, let me disable this and go back to the first one. And you know, what are the troubles that occur in the lab in a circuit like this? For example, you assume minus 620, right? So suppose you have not made this non-inverting terminal which is properly grounded, right? So if I just take it out, what do you get here? Minus 13.9, right? The op-amp is saturated. So typical errors with an op-amp that you get, is you find that the op-amp is saturated. Why? Because of some wrong connection. So if I don't ground properly, you can see it saturates. If somehow this connection, let's say if I remove it, again, saturation, 13.9. So a typical error in an op-amp manifests itself typically as the op-amp is saturated. Now in this case, it's not saturated, right? In this case, let's go back to this one here. In this case, it's not saturated. The op-amp is not saturated. And then the other thing is, if the circuit were to function properly, you know, if you take an op-amp and you have a negative feedback, then this point should be virtual ground. Right? Virtual ground meaning experimentally, if you try and measure, it would be a very low value. On an oscilloscope, it would be difficult to measure. This value is 2.9 volts. Right? It's very high positive voltage. So we checked here and we said this is also a large positive voltage here. So what is really going on? The op-amp is fine. You've replaced it twice, thrice. There's no problem with the op-amp. Everything is fine here. Everything looks, the connections have been made properly. You can double check this connection here, double check all of that. Everything seems to be fine. But in this circuit, you're getting a positive voltage here. The issue is why? What could be going wrong? Right? Huh? No, power supply is also fine. You check, right? You go and check. There is indeed plus 12. There is indeed minus 12. Power supply is also fine. So op-amp is fine. Power supplies are fine. Diode is connected in the right manner. We took out the diode and we put a resistor there, right? It's still if you put a resistor here, you would expect some kind of a negative voltage here, right? Still positive voltage. Still positive voltage, no virtual ground, right? So what could be going wrong? So that's an opportunity now to learn that besides op-amp saturating, there's another thing that can go wrong in an op-amp. And what can go wrong in an op-amp, which is true of all circuits, is every component has a current handling capability, maximum current that the component can handle. If you try to force more current through it than what it can handle, it will not behave properly. So our op-amp here has a current handling capability of around 20-25 milliamperes. Okay, 20 to 25 milliamperes is the maximum current that your op-amp can handle. A 7-for-1 op-amp. Other op-amps can handle more or less. It varies from op-amp to op-amp here. So this can handle a maximum current of, let's say, 25 milliamperes. And then, so the thing was, after looking at it, was that is that current limit getting violated, right? So we checked what is the value of resistor here, right? What is the value of resistor here? So if I double click it, deliberately I hid it from you. What is the value of resistor here? So let me put it value here, right? 100 ohms. They had connected 100 ohms. So now 5 volt, if this were to be a virtual ground, 5 volt here, 100 here, you're pushing 50 milliampere current into it. You're trying to push 50 milliamperes current. The op-amp, the current that can flow in the op-amp here, eventually the current comes here and goes into is maximum of 25. So imagine now the maximum current that can flow is 25. So if you have 5 minus 25 milliamperes multiplied by this, you'll get obviously some positive voltage here. So it's not working properly because you're violating the current limit. And you can see here, if I just double click on this and change, it works fine now. So if I put another 0 here, right, works fine. Now the current limit is no longer being violated. It's 5 milliamperes, everything works fine. But if I go ahead and do again back to this, I'm violating the current limit. .26. Now this is where, so it's happening because this is a practical, a real op-amp, right? It has a current limitation. Now if I double click on this and look at the model level here, when you have a level 3, so level 3 is an accurate model. If I change it to level 1, then it becomes an ideal op-amp, right? So in an ideal op-amp, none of that will happen. Right? So works fine. Ideal op-amp, 50 milliamperes, it works fine. You can push in 5 amperes, it will work fine. Any amount of current that you put into an ideal op-amp, it will work fine. Right? But the moment you make it now a practical op-amp with current limitations and all that, it doesn't work. So this is what was happening. So the lesson from here is that every op-amp has a current limitation. If you try to force more current than the current it can handle, then all these problems are likely to occur. All right, so that's something to be aware of. Now, these things can occur in many different ways. For example, let me go back and let's push it back to, let's make it a practical op-amp here. Let's make here 1000, right? So everything is working fine. Okay, everything is working fine. But now, this is not just from this side. What I could do is, let's see what happens here if I connect a load here. All right, no problem. Everything is fine. Whether it's 10K, let's change it to 1K. All right, as I go from 10K to 1K, no change here, which is expected, right? There is a load that I've connected here, and the op-amp has very low output impedance, extremely low output impedance. So, whatever load I connect, nothing is changing. Well, just for Oh, 11K I put. Let me put 1.1K. All right, it's still minus 622, no problem. Let's change the current to, let's change it to 100 ohms. Still nothing, minus 622 works fine. Okay, you think it will ever change? Let's change it to 10 ohms. If I put 10 ohms now, look at the value, minus 160 millivolt. It was supposed to be some minus 600, right? It's become minus that value here. But Opamp has in fact, Opamp has a output impedance which is lower than this, especially with feedback. So what is really happening here? Well, if you look at the current, can you see what is happening here? This current is how much? 16. And the current coming from here? 4.5. The two currents will add up, and what is the current going into the op-amp? Around 20. You are reaching the current limit again. So the distortion is occurring because if you connect a very low value of load resistor, there would be a lot more current here. It would require a lot more current here. Where does this current have to come from? Well, if this is not supplying the current eventually has to come from the op-amp, and the op-amp has a finite limit. So again, if you connect load resistor and then you put a very low value of load resistor for this thing, then again you will see a problem occurring. Right? So if you put 1K, 10K, 100K, no problem. But if you put a lower value of load resistor, because of the current limitation, this issue will come here. All right, so this can come from various sides. It could come from here because you're trying to pump in more current, or you're trying to draw or more current from the load side. Either way, you're imposing a burden on the op-amp which is more than what it can bear. It has a current limit of a certain value that you have to obey, right? So that's the message part here of this particular one here.